Hello everyone, we come up with the paper review academic seminar. The paper is variation of tropical cyclone season start in the western North Pacific. The group of authors here is Kim Deong Kim, Heung Sung Park, and journal name is Journal of Climate. This paper is published in 2017. The first is introduction. As we know, the western North Pacific is most active tropical cyclone basin. It occupies about 30% of global TC of the world. Second is TC activity is modulated by large-scale environmental parameters such as sea surface temperatures, vertical wind shear, and vorticity, and so on, even though the humidity. And these environmental parameters vary seasonally, and thus it can induce changes in seasonality of TC activity. And we know that a TC activity feature including start, end, and length of the TC season. For instance, I give an example. No TC formed before July in 2016, whereas 9 TCs occur before July in 2015. What's the reason cause this different in 2016 and 2015? This can be due to changes in environmental parameters such as sea surface temperature and wind shear. Thus, it's worthwhile to examine variation of TC season in the WNP and the large-scale environmental parameters affecting them. Objective of this paper is to examine the variation of TC season in the western North Pacific and large-scale environmental parameters. In other words, we study the relationship between the TC feature, includes TC start date, TC end date, and length of TC season with environmental variable, including the sea surface temperature, relative vorticity, humidity, and so on. We should have some definition. First is TC formation date. What is TC formation date? In this table shows a different type of category of TC intensity. This is minimum pressure is close to center of TC. This maximum wind speeds. Based on this criteria, they categorize into different intensity of TC. This is lowest intensity, this is medium, and this is the highest intensity. So the TC formation date is defined as the day when the TC first reaches maximum wind speeds over 17 meters per second. So it's corresponding with this threshold category, this category of intensity. I will give you an example to demonstrate that. For example, actually this TC formed in this place, but it was not considered as a TC formation date here because its intensity here is lower than this threshold. It's in this threshold. It's in this category. So after formation is moving in this way, and in this play it's a yellow color. It's the first time the first time TC reached maximum wind speed over 17 meters per second in this threshold. So it's called this play is satisfy this threshold of intensity. So this play called and TC formation date in the 23rd October. Another definition is TC year or TC season, and its TC season start in the 1st February in current year and finish in 31st of January in next year. So before May is called early stormy season, and after November is called late stormy season. And this period from May to November is called the big stormy season because most of the season number occur in this period, around 70% of TC. This is result analysis. The whisker box show how TC season activate. This dot is the first TC and this dot is last TC. The start date of TC season defined as the 5 percentile of data, and the end date of TC season defined as 95 percentile of data. And the y-axis shows the day of TC year or the day of TC season. For example, 50 days is equivalent 2 months, 100 days corresponding 3 months and 5 months, 6 months, and whole TC years. And we have many years, so we have many whisker boxes. And this line shows us the start date is corresponding this threshold, but it's average every year. So this line shows the end date is corresponding the 95%, this threshold, but it's average for many years. So the figure shows that start date tend to be later from here to here. From this period to this period, the starting date tend to increase. It means it tend to be later. It means stormy season tend to become later during this period. In contrast, the end date tend to be earlier. Yes, it's decreased tendency, so it means it earlier. Another word is stormy season tend to finish sooner during this period. Sooner. It means that the length of stormy season tend to be shorter. Yes, in this period, so we can see shorter than this period. Yes. However, this change is not significantly important. This table shows us season start for average is start in 18 May. Season end for average is finished in 27 November. The season length for average is around 193 days. It's corresponding 6 months. And season start and season length, they have standard deviation around 35 days. It means season start and season length is widely fluctuate. Yeah. But season end has standard deviation only around 18 days. It means season end has slightly fluctuate only 2 weeks. The correlation, this table shows correlation between the correlation between the season length and the season start is significantly important. 99% of significantly important, but other cannot. It means that season length maybe only depends on the variation of season start. Yeah, the the negative correlation means when the season start comes late, length of this season is shorter. But in contrast, when the season start comes soon, its length of this season is longer. Because this result favorable for the relationship between the variation of season length and season start, so the further analysis will focus on the variation of start of this season. This slide I will explain you the effect of several environmental factors on TC development. First is sea surface temperature. How sea surface temperature affects on TC development. For example, this is warm ocean. Warm ocean heat low level air mass. It makes a low level air mass hotter, so it increases the convection. Convection increases cloud formation. So this process, convection process, is favorable for TC development. In contrast, if the cold ocean it makes the air mass is colder, so it's suppress convection, so it's not favorable for TC development. About the low level vorticity, if vorticity is more than zero, the conversion, it means we have conversion condition in low level. The conversion in low level, so the air should move up in high level. So it means it's conversion in low level increases convection, so creates a cloud. This process also favorable for TC development. But the TC vorticity is less than zero. It means diversion in low level. So it cannot have convection in the high level. So this process is not favorable, suppress TC development. This slide shows us a correlation between the TC season start and environmental parameters. The left column is a correlation between TC season starts and the environmental parameters, but for DJF means December, January and February preceding years. The right column is similarly, but for March, April and May. The first panel shows the correlation between the TC season start and the SST, sea surface temperature. We can see there are two centers of positive correlation. The first center is Central Eastern Pacific, and the second center is Indian Ocean, high positive correlation. Especially this pattern of SST corresponding to the El Nino and La Nina phase. It means that this result shows us in El Nino years TC start dates are later, but in contrast in La Nina years TC start dates are earlier. It's a contrasting pattern between El Nino and La Nina years. And the second is we consider geopotential high. In geopotential high, we have positive correlation in almost whole domain. It means that in with anticyclone anomaly of geopotential high, we have late TC start dates. In contrast, if cyclone anomaly of geopotential high, we have early TC start dates. It's very clear. So we can understand in similar way for vorticity. This slide shows us how the start date of TC season respond to the El Nino and La Nina years. In this table show us in El Nino year we have start date of TC season around May, June, even though July. But in La Nina years, the start date of TC season around April and May. It means that in El Nino year, start date of TC season come later. But in La Nina year, start date of TC season come earlier. Conclusion, the results show that the length of TC season is highly modulated by TC season start rather than its end. Secondly, start of the TC season in WNP has large interannual variation closely associated with the variation of sea surface temperature in Indian Ocean and Central Eastern Pacific. The third is when ST of Indian Ocean and Central Eastern Pacific are warm in preceding winter associated with anomalous high pressure and anticyclone circulation um, in the following spring, resulting late start of the TC season. The opposite is right for the cold phase. The last is this results success in a strong El Nino year in the preceding winter significantly delays the TC season start in the following years.